This video is going to review the various methods we use for sampling organic vapors in class, and it'll also be kind of a preparation for you for assignment 5, when you have to submit some results for VOC calculations, involving some VOC calculations. Okay, so for starters, we looked at primarily 3 ways of measuring VOCs in the air. One is the use of sorbent tubes, where we draw air through a material that tends to absorb organic materials, organic vapors, such as activated charcoal, 10X, a number of them. Activated charcoal most commonly. Okay, the activated charcoal absorbs the VOC. It collects in this sample section, 100 milligrams of absorbent material in this case. There's a backing part where there's another 50 milligrams of material, where you can tell that in case it didn't catch all of the VOCs, in case it got saturated or you were moving air through here too fast for it to get completely absorbed, you would then find it in this backing area here. That would be some concern, because that would tell you that you didn't really capture all of it, so your answer might not be accurate. So the lab that you send this off to that analyzes this for the VOC that's present and measures how much is there, they're gonna analyze both sections separately and report back to you if there's an excessive amount of that VOC that you were trying to capture in the backing section. So we have sorbent tubes. The other method we looked at was a direct reading method, which is the use of colorimetric tubes. In this case, tubes that are manufactured by a company called Draeger. There's a similar company called American Sensodyne that makes another kind of pump, but also similar tubes. The tubes are graduated, and there are material in them that reacts to whatever specific contaminant might be in the air. Some cases, in many cases, it's a VOC, acetone, toluene, benzene, so on and so forth. But you can buy tubes for hundreds of different compounds. In fact, some of these tubes are for non-organic chemicals, acid gases, hydrochloric acid, so on and so forth, sulfuric acid, right, as well. But many of them are for VOCs as well. So that's another technique we can use. Not very accurate, but it's a good screening method. Okay, so the third method we looked at was the use of a photoionization detector. Okay, and that is a direct reading instrument. Air is sucked in through the instrument. There's a photoionization cell, basically a cell where a very strong UV source, ultraviolet light source, exposes the gas that's coming through here, the air and the gas that's coming through here. The outer shell of electrons are excited or moved off, creates ions and ionizes that organic material, which makes the air passing through here more conductive. And this can read that conductivity, that increase in conductivity, and feed back to you how much of that VOC was present in the air. It has to be calibrated. It's typically calibrated to a single material, isobutylene in most cases, but then you can adjust your readings for many other VOCs. Usually the manufacturer will provide a catalog that'll tell you that if you've calibrated it so it correctly reads 100 ppm of isobutylene, that if you're measuring toluene, that if you apply a correction factor like 50% or 200% to that reading, it will correctly tell you how much of that other VOC is in the air. The one we use has a 10.6 electron volt lab. That's the energy level that the UV source can provide. Some materials can be detected with this that level of energy. Some may need more or less energy as well. So you can get a catalog from the manufacturer of what compounds that this is capable to detect. There is another one I didn't have a picture of right now, but it's you can collect air samples in a evacuated stainless steel canister, very often called the Suma canister, because that was one of the first manufacturers of those types of devices. You literally can open a valve, suck air into this evacuated empty vessel container, and send it to a lab, and then they can analyze it. We're going to talk about that more when we get into indoor air quality, because it isn't a commonly used indoor air quality technique to survey for a number of VOCs that that are typical in indoor air. There's a method called TO15 or TO17 that we're going to look at when we get to indoor air quality. So getting back to the main exercise that we were involved in, okay, we set up a sample tray using a sorbent tube. Most of the time, these sorbent tubes are covered with a protective tube cover. They don't serve any other function than to be able to clip this thing easily to the collar and to protect the tube from damage. We can have a flow control, adjustable flow control, a little screw and needle valve that is on that protective, just after that protective cover, or it can be in another place on the pump. And we also use very frequently a constant pressure controller, a device that evens out the pressure and the flow when you use these low flow pumps at very low volumes. Typically in VOCs, we're sampling at very low volumes because we have to go slowly through that activated charcoal to make sure that the sorbent material absorbs all of the VOC. So we're usually running in the range of hundreds of milliliters per minute rather than thousands or liters per minute. And so this is typical of a sampling tray. We wind up on the worker, they pump it on the worker's belt, and they could wear this for whatever period of time that we felt that was needed to correctly evaluate the level of exposure for the worker to a VOC. There's another look at it. In this particular case, you'll notice that we have a single pump. There's a little pressure controller. We have a single pump, but we have two tubes connected to it. This is part of the calibration process. Notice we're connected to the tube, and we have the pump on. We're adjusting the volume that's flowing through the tube. We have two of them set up. Each has its own separate needle valve. So we can set one tube to collect air at the rate of 200 milliliters per minute, and we can set the other tube to collect air at the rate of, say, 100 liters per minute. That increases our chances of making sure that we get a good sample without breakthrough, and that we collect enough material. So it's a little bit more reliable than just using a single tube, where you might get breakthrough. In other words, you saturate the sorbent tube. If there's too much VOC, more VOC in the air than you anticipated, or you don't that sample if there's less VOC in the air than you anticipated. So it's pretty good practice to do this kind of thing. This setup is the calibration process. This is the equivalent to the dry cals that we use in our lab exercise. And this is that SKC pump, same pump that we use. Here's a little bit closer look at a typical twin port sampler, and the screws that you adjust, you can't see them here, they're on the side. In other words, if you follow my arrow here, it's on the side there and the side there for each of those two tubes. And this, in fact, takes the place of your protective cover and clip to put it on the worker. Okay, so here's the typical calibration setup, similar to what we just saw up there. And so for our purposes, we did some basic exercises where we set up sample train and so on and so forth. We didn't actually send out samples for results. In our lab, in the lab description, we discussed how we would have simulated this using a sampling chamber. One of the things now that you were asked to do in the assignment number 5 is to do a calculation that involved a sampling period, a evaluation of what the level of VOC was based on the lab results that you got back from your sorbent tube. In case you didn't record it, this is one of the air check pumps with a model number and serial number. If you didn't record it, you can just use this picture in place of what you had. So we're going to do some calculations now. Here's the formula that we're going to use. Typically, the lab will send you back results in the form of milligrams that they found on the sorbent tube, or if you tell them the volume rate and the time that you ran the sample, they'll even calculate it in terms of milligrams per cubic meter for you. Okay, but not always. Sometimes they'll just tell you how many milligrams of the material was present. This formula will help you convert the lab's reading to parts per million. And the reason why we're interested in that is because very frequently the OSHA permissible exposure level or the threshold limit value are very frequently expressed as parts per million rather than milligrams per cubic meter. So it's handy to be able to know how to do this calculation. So you'll be able to use your milligrams per cubic meter from the lab report, 24.45. Those of you that are astute about this will recognize that that has something to do with the mole liter volume equivalence for a VOC or for any gas. And that would be divided by the molecular weight of the VOC. That would depend on each individual VOC. So let's go ahead and take a look at the exercise from class. Okay, so let's take a look at the lab that we simulated, where we set up our sampling stream. We simulated a sampling of VOCs in the air. We also tested the performance of the PID and our sorbent tubes using isopropyl alcohol and so on and so forth. Let's take a look at a simulation of such a lab. So here we're going through the process of using these various devices, including a sorbent tube and a low flow pump to actually sample the air. At the end of this, you're asked to complete an exercise. Okay, here we go. Here's our exercise. That's complete. In this case, we're talking about sampling the air for acetone. Happens to be the what we use for this particular example. Okay, so now first thing to ask you for is to identify the pump, the equipment that you use, so if there's any issues with it, and so on and so forth. So I'm gonna, you may have written it down as we were playing around with the pumps. If you didn't, you can use this image if you want to get the pump ID number. We identified this as pump 3. I'm going to put down the make and model number. Check. XR 5000. Okay, and I'm going to actually include the serial number. Typically, you want to include the serial number as well in case you have to track back to any issues you might have with equipment, or you want to check to make sure it was calibrated. Yeah, in this particular way, we reference the NIOSH procedure for sampling for acetone, and it recommended use of an activated charcoal sorbent tube. Okay, different VOC might use a different one. Activated charcoal, obviously the most common one. We ran the pump, we calibrated the pump with the tube and the flow regulator in place. We calibrated it before we actually did any sampling. We took 3 readings, say for instance, it might have been 0.20, 0.21, and 0.22. We averaged those 3 readings and it came out to be 0.21. Okay, so then we did a post calibration, and our post calibration, the average came out to be 0.20. So the average flow rate was actually 0.205 in this particular case. We sampled using a simulated environmental chamber. We sampled that area or work area for 45 minutes from 7 o'clock to 7:45. And then we determined what our actual sample volume was. Well, since the average flow rate was 0.205, right, the average of pre-calibration and post-calibration, the average flow rate is from 3 to 5. This is going to be equal to 45 minutes times the flow rate. In other words, 0.205 liters per minute. Okay, and in fact, you could say that this is minutes, and you can see that minutes cancels out, and this turns out to be, okay, let me go ahead and give you that number. Okay, this in our case, in our class example, this turns out to be, let's clear this out. Okay, let's say 45 times 0.205 is equal to, whoops, 45 times 0.205. That comes out to be 9.25 liters. Equals 9.25 liters. 225 liters. I'm not gonna round. I'm gonna wait till the very end if I do any rounding. I'm just going to carry that number over. I can use my calculator or Excel, so there's really no need for me to, not going to save me that much work. Okay, so let's take a look at this. We send that sorbent tube through which we pulled 9.225 liters of air through to a laboratory, then, a little sensitive here, the laboratory determines that there was 14.5 milligrams of acetone in that sample. We looked up and we know that the molecular weight of acetone is 58. So that sample, that sorbent tube had 14.5 milligrams of acetone present. So now we need to convert that into milligrams per cubic meter. Okay, so in fact, we actually sampled only 9.225 liters. We know that there's a much more, that there would be much more at this concentration, there would be much more than 14.5 milligrams of acetone in the air that this was exposed to. Well, how much, if there was 14.5 milligrams of acetone in 9.25 liters of air, how much was there in a cubic meter? A cubic meter is 1,000 liters of air. So we can actually go ahead and do that calculation quickly. So I'm going to set it up as a ratio. We have go back to this for a second. We found 9.225 milligrams in okay, so let's continue with our calculation. We found in not in 9.225 liters of air, we found 14.5 milligrams of acetone. So 14.5 milligrams of acetone was present in the 9.225 liters of air that we sampled. We want to convert that into how much was in a cubic meter. Now, cubic meter contains 1,000 liters, not 9.225. So we need to know how many milligrams were present in that 1,000, would have been in that 1,000 liters of air rather than 9.225. So we cross multiply 9.225 liters times X is equal to 14.5 milligrams times 1,000 liters. Okay, so we multiply this out, divide by 9.225. Divide this side by 9.225 as well. And we wind up with, let's do our calculation here. Here's our calculator. And I'll clear this out. So 14.5 times 1,000 equals 14,500 divided by 9.225, and we wind up with 1,571.8 milligrams. Would have been, if we had, so this is what we would have collected if we sampled the entire cubic meter, 1,571.8, okay, milligrams. Okay, so now, notice that this is liters. Liters cancel out, these are milligrams. Okay, so now we have to figure out, well, that's milligrams per meter cubed. Now we have to convert that to parts per million in case we want to look up the PEL or TLV. Okay, so let's take a look at how we would do that. So I'm going to go back to our PowerPoint and our formula. And our formula tells us if we take that 1571, I'm going to use 1572 to make things a little quicker. Okay. So we take our 1,572 milligrams per meter cubed, right? Our milligrams per meter cubed, times 24.45. Those of you that are chemists will recognize that as the mole volume equivalent. Yeah, 1 mole of any gas or VOC is going to take a standard temperature pressure is going to take up that number of liters divided by the molecular weight of this VOC. In this case, it's acetone, and I think we said we defined it as 58. Okay, so let's see what we wind up now in terms of parts per million. 1,571. Notice even though I wrote it down as 2, I'm actually keeping the rest of this times 24.45 equals divided by 58. How many ppm do we have? We have 662 parts per million. Okay, so let's look up go to Google, look up the time weighted, the permissible exposure limit, OSHA permissible exposure limit for acetone, and I see that it's 1,000. So we are below the OSHA permissible exposure limit. 662 is of some concern though, because we only sample for 45 minutes, not a full 8-hour workplace exposure. It could vary considerably. We only sample one particular day. The worker's exposure at this level, I'd be a little bit concerned that there may be times that this level would suggest there may be times when the worker's exposure might exceed the OSHA PEL. Not only that, the other consideration is that the California PEL is 500, and the NIOSH recommended exposure limit is 250, as is the ACGIH threshold limit value of 250. So even though you haven't exceeded the PEL, you have exceeded the threshold limit value, which suggests at that level that you might start to see some health effects. Okay, so we're going to next, so this is quickly look at the exercise. I made a few corrections on here to make it a little bit clearer. In this case, we're looking at isopropyl alcohol, isopropanol. Okay, again, put in the pump ID, pump make, media, and so on and so forth. I left the volumes the same, so you should be able to get through that and calculate out your actual total volume sampled. And then I left for you, I told you that we found 14.5 milligrams of isopropanol. Coincidentally, the same thing we found before, except this time it's for a different compound, which is going to have a different molecular weight. So I'm going to leave it to you to go through the same exercise we did before, calculate the molecular weight, convert the volume the number of milligrams that you collect in your sampling tube, and how much would have been in a full cubic meter, 1,000 liters. Okay, and then go down here and answer a few questions about it. What was the concentration that you found? If the lab reported that amount in the sorbent tube, calculate that in ppm. How would you expect charcoal passive sampler and direct reading instruments to compare with this? Okay, so I think we discussed the accuracy of passive samples like that, like our sorbent tube pump or those badges, and how that compared with how accurate this method would be, and how accurate our direct reading instrument, such as a PID, might be. PID might be pretty accurate, right? So discuss the different other methods that we talked about using, and which you think might be less or more accurate. Identify potential causes for sampling error during the lab exercise. I know what I think we get wrong most of the time. What part of this measurement we get wrong most of the time. I'll leave it up to you to suggest to me what you think it is. And how does this concentration compare to the OSHA PEL and ACGIH TLV for isopropyl alcohol? Okay, and I left a formula in here just so you didn't have to go running around somewhere to get it. Make sure you use the updated version in this. I'll put March 14th on in the sample, in the file name for this as well. Okay, so hopefully that helps a bit on this exercise and prepares you for a future where you might actually have to do samples and do calculations like this.